n, and n. Here, they're just the numbers, constants. And so you cannot change that. But the only thing you can change is x, including the c is a constant. So in this series, you can always change x value for different numbers. So then if you plug in some number for x, you get the one series. If you plug in another value for x, you get another series. Then you get a bunch of series for different values of x. And some of those series we got for different values of x may converge, but the other series for the other values of x will not converge. Then we have the convergence radius, or radius of convergence, something, so in general, a power series will converge inside the interval with some radius centered at C, and then number 9, if you recall that. And then, we're only interested in the convergent power series. If you pick up any value for x inside that interval under number 9, to plug into the power series, the series is convergent, and we get the finite and definite number for the sum of this infinite series. So if you change another value for x, still pick up the value inside the interval, then you will get another convergent series, which gives you another sum. So then we actually get a function of x from the series. Okay, for each value of x, if we plug it into the power series, you get the value, and then for another number of value of x, you get another value for the sum of the series. So that actually defines a function of x, the power series itself. So it defines a function of x. But that means we can call this power series an times x to the minus c to the n, sum up with n starting from 0 to infinity. We call this power series f of x. Okay, it is a function of x when it converges. Okay, and so then the other question is, given any function f, can you find a power series to represent it? So this is the question backward. We just said for any convergent power series, it defines a function. All right. Then the backward question is, for any function f, can we find a power series for itself? Okay. So this is the theorem 22 in this chapter. It tells them that we do write any function in terms of a power series, and that we can do that. And that series is called a Taylor series. Okay. So what it says in this theorem is, if f of x is represented by a power series, that means the function f is the same as the power series. They are equal. Okay, within the interval of convergence of this power series. So for all x in the open interval I containing c, so that's called the interval of convergence we talked about last time. Then there's a relation between the coefficients of the terms in the power series with the function itself. Okay, so what it means is, for any specific function f, those ans, those coefficients, are uniquely determined from the function itself. Okay, You cannot find two different power series for the same function. There's only one power series for any specific function. And you know, you can assign any value for C by choice. Okay, so you choose the value C, and then you find the power series coefficients of the power series an from the function f and C. So so then you can represent the function f by different power series depending on the value C. Okay, so if you let C equal to 0, then you get a power series. If you get C equal to, if you let C equal to 1, and then you get another power series for the f, but they're all equal to f. So the question is, what value you want to choose for C? And depending on the uh, uh, situation, you want to choose C for different values. That's determined by the real world problem. Okay, but in any case, C is a number you choose. All right. Then if X is defined, is specified, and C is chosen, and you can find the coefficients of the power series for the function f using the formula of an equals the nth derivative of f evaluated at C over n factorial. Okay. So then you can write fx equal to the sum of the series of f and the nth derivative of f evaluated at C over n factorial times x minus c to the n. If you plug in the nth derivative of f evaluated at C over n factorial for an in the power series, you're going to get this. So if you write each term explicitly for this power series, you're going to get f of c plus f prime c times x minus c plus f double prime c over 2 factorial times x minus 2 square. And then f triple c, the third derivative f, evaluated at c over 3 factorial. So in general, the term will be the nth derivative of f evaluated at c over n factorial times x minus c to the nth power. So this is the thing you get. When n equals 0, for example, then you don't take the derivative. So it's just the f of c over 0's derivative. But 0's derivative is 1, so you get f of c, and the x minus c to the 0 is also 1. So the first term will be x minus will be f of c itself. The second term, you take n equal to 1, so you're going to get the f prime c over 1 factorial, which is 1, and x minus c to the 1th power, which is x minus c, as you see. And the next term is n equal to 2, so you get the f double prime at c over 2 factorial times x minus c squared, and so on. So this gives you a power series representation of a function. That means you can always write a function, any function we learned, a linear function, a quadratic function, power functions, polynomials, rational functions, trivial functions, exponential functions, logarithmic functions, any function you can always represent, you can always rewrite this function as an infinite sum of power functions like this. So this is called power function expansion of a function f. Or sometimes we call it Taylor series from the mathematician's name, Taylor. Okay. So what is Taylor series? It's just a power series representation of any function. Okay. You can rewrite the function f by a sum of infinitely power functions like this. All right, and then you can choose any value of C to represent this function. For each value you choose for C, you're going to get a different representation. You're going to get a different power series. All right. So now when you choose C equal to 0, that's called the Maclaurin series. Okay, as I said, you can choose any value C to represent the function, but when you choose different values of C, you get different representations of the function. So specifically, when you choose C equal to 0, then you get a series called the Maclaurin series for that specific series. For each value of C, you get a different series. When C equal to 0, that series is called the Maclaurin series. Okay. Any questions? Does that make sense? Okay, let me just do one example to make it a little more clear about the idea in here. Okay, let's just define the Maclaurin series for f equal to sine of x. So what it means is we want to rewrite this function sine x by a sum of power series. Okay. So when we say Maclaurin series, it automatically means C equal to 0. We can choose any value for C for the Taylor series. So in the case of Maclaurin series, C equal to 0. So then, according to the theorem, then we have f of x equal to the sum of nth power of f evaluated at x equal to 0 over n factorial times x to the n. C equal to 0, so x minus c is just x minus 0, which is x itself. So you get x to the n itself. So if you write this series explicitly, it's just f of 0 plus the first derivative of f evaluated at 0 times x plus second derivative of f evaluated at 0 over 2 factorial times x squared, and the third derivative of f evaluated at 0 over 3 factorial times x cubed, and plus all the terms with the power of x to the n. So that's what the Maclaurin series looks like. Okay, so each term in the series is just the power of x itself, the integer power of f plus a constant term in the first place, right? So we just need to figure out exactly what the series itself, what are the numbers in this series, So that means we need to figure out the f of 0, f prime 0, f dot 1 0, f triple 0, and so on. All of those numbers we need to figure out. Okay, so let's just do it one by one. So the function f is sine x. So f of 0 is sine 0, which is 0. So the first term, f of 0 in the series is 0. Okay. And then the second term, f prime, take the derivative sine x to get cosine x, and then you plug in 0 for x. So f prime 0 is just cosine 0, which is 1. And then you can also do f double prime x. Oh, I don't know why I wrote like this in here. It's not exploring the x. So this is a typo in here. So we need to take the second derivative. So you just take the derivative of the first derivative. So you take the derivative of cosine x, you get a negative sine x, and then plug in 0 for x. So we get the f double prime 0 equals negative sine 0, which is also 0. And then f triple x, I just take the derivative of f double prime. We get a negative cosine x. And then plug 0 for x, we get a f triple 0, and that's negative cosine 0, so that's negative 1. And then you can do, continue to do that. The fourth derivative of f, so we just take the derivative of third derivative of f. So you take the derivative of negative cosine x, you get the positive sine x. Okay, if you do that, because you got the derivative of cosine x to be negative sine x, but you got another negative in the front, so that becomes positive itself. So then you plug in 0, so you get the sine 0 equal to 0. That's the fourth derivative of f. And then you take the fifth derivative of x, which is the derivative of the fourth derivative of f. So you take the derivative of sine x with cosine x. So that's just cosine 0 if we plug in 0 for x, which is 1. So you can see there's a pattern here for those derivatives. We actually come back to the first derivative, right? If you look at the fifth derivative of the function, it's just the first derivative, cosine is the same. And the fourth derivative of f, we just got the same as the function itself, f of x. So if you continue to take the derivatives, then you just repeat those four functions. So you're gonna get the next thing, you're gonna get a negative sine x, and then the next thing next it will be negative cosine x, and so on. So we don't have to repeat everything. So we know the pattern now. So then what you're gonna get is 0, 1, 0, negative 1, and 0, 1, 0, negative 1. So it's just repeat those forms. Okay, 0, 1, 0, negative 1, right? For those derivatives. So you just plug in those numbers into the series. Okay, so again, f of x equal to f of 0 plus f prime 0 x plus f double prime 0 over 2 factorial x plus f triple 0 over 3 factorial times x cubed, and so on. So just plug in those derivatives values in here. So the first term, f of 0 is just 0. F prime 0 is 1, so we get the 0 plus 1 times x plus f double prime 0, which is also 0, so we get 0 with 2 factorial x squared. And the next term is f triple 0 with 3 factorial times x cubed, and the f triple 0 is just negative 1, so we get negative 1 over 3 factorial x cubed. And then you just repeat the pattern of those derivatives. So the next term is x to the fourth will be the fourth derivative of f will evaluate as 0, so that's 0 over 4 factorial times x to the fourth, and then plus fifth derivative of f evaluated at 0, which is 1 over fifth factorial times x to the 5, and so on. Okay, so then you can see there are half of the terms vanishing. Okay, the first term, the third term, and the fifth term, and so on. So what is left? It's just the x. So 1 times x is just x, the second term, and the fourth term is negative 1/3 factorial x cubed, and then the next term will be 1 plus 1 over 5x to the 5. But then the next term will be negative. Okay, so it just comes like a positive, negative, positive, negative, like this. Okay, and the only left with all the powers of x, x cubed, x to the 5, all the odd powers, all the even powers vanish. And then the coefficient is just 1 over factorial, like this, with plus and minus, okay. So if you rewrite this whole series in sigma notation, it will be like this: negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. with n starting from 0 to infinity. Okay, so you can easily check that by plugging the different numbers for n. So for example, the first term starts from x equal to 0, so you're going to get the negative 1 to the 0, which is 1, positive 1, and to the x to the times x to the 2 times 0 plus 1, so 2 times 0 plus 1 is just 1, so you get this 1 times x to the 1, which is just the x on the top, and then the denominator is 2 times 0 plus 1 factorial, so that's 1 factorial, which is 1 itself. So then x over 1 is just x, so that gives the first term x. And the next term, you plug in n equal to 1, so you get the negative 1 to the 1, so that's negative, and times x to the 2 times 1 plus 1, 2 times 1 plus 1 is just 3, so you get x cubed over 2 times 1 plus 1 is just 3 factorial. 3 factorial, right? So you get negative 1 over 3 x, 3 factorial x cubed. And the next term you plug in n equal to 2, so you get negative 1 squared, which is positive 1, times x to the 2 times 2 plus 1. 2 times 2 plus 1 is 5. So that's just 1 times x to 5. And then in the denominator, you get 2 times 2 plus 1 factorial, which is 5 factorial. So that's a part term with 1 over 5 factorial x to 5, and so on. Okay, so this is just the rewrite this terms of the series in a compact form. Any questions for this example? So, so this is the Maclaurin series for the sin x. Okay, so in other words, sin x is equal to x minus 1/3 1 over factorial x cubed plus 1 over 5 x to the 5 minus 1 over 7 factorial x to the 7 plus all of those terms in the tail. They are exactly the same. Okay. Okay, so let's see on the next page. So so we can use those Maclaurin series for those basic functions to rewrite Maclaurin series of other functions. Okay, so in this example, we need to find the Maclaurin series for another function f equals 2 times sine x cubed. Okay, so let me just write down sine x equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial times x to the 7 and so on in the compact form by sigma notation from last example on the previous page. Now, to find the Maclaurin series for f equal to 2 sine x cubed, you don't have to use the definition to take all the derivatives as we did in the previous example. You know, do the first derivative, second derivative, third derivative, and the fourth derivative, fifth derivative, and so on. You don't have to do that. And actually, if you do in that way, it makes it really, really complicated. But fortunately, we already have the Maclaurin series for sine x, as I just wrote in here. So we can use that to find the Maclaurin series for this f, which is 2 times sine x cubed. So what you do is you just replace x by x cubed in the Maclaurin series for sine x. Okay, so then you get a sine x cubed equals x cubed minus 1 over 3 factorial x cubed to the cube plus 1 over 5 factorial x cubed to the fifth minus 1 over 7 factorial x to the cube to the seventh and so on. So you can see you just plug in x cubed in x in this Maclaurin series for sine x on the formula. right? So in the sigma notation in the compact form, you just place x by x cubed. So you're going to get -1 to the n times x cubed to the 2n plus 1 over 2n plus 1 factorial. So just do a little simplification. You know, x3 to the 3 is just the x cube, x to the 9, and x cubed to the 5th is the x to the 15. Remember, you need to multiply those two exponents. And in general, x cubed to the 2n plus 1, just multiply 3 with 2n plus 1 in the exponent. So you get the 6n plus 3 if you distribute 3, right? So it becomes the sum of -1 to the n times x to the 6n plus 3 over 2n plus 1 factorial with n starting from 0 to infinity. So that's the Maclaurin series for sine x cubed. It means you write sine x cubed as a sum of power series of x, right? So that's what it means by Maclaurin series. You don't have anything in C, so just power function of x. And then, you know, what we need is f equal to 2 sine cubed. So you just multiply 2 to the whole thing. So you get 2 sine x cubed equals 2x cubed minus 2 over 3 factorial x 9 plus 2 over 5 factorial x to the 15th and so on. Or you can write in the sigma notation as 2 times -1 to the n x to the 6n plus 3 over 2n plus 1 factorial with n starting from 0 to infinity. So that's the final answer. Okay. You just rewrite this function by a series of power functions of x with positive integer exponents for x. Any questions for this section? So we're done with this section, and we got 6 more minutes. I think we can do one more section, which is 10.1. That's really short. So why don't we just do it? Maybe we don't have any questions. I think there's only 2 pages in this section. It's really simple. So we finished the chapter 9. We're going to do a few sections in chapter 10. Chapter 10 is about the conics, parametric equation, the polar coordinates. Okay, so we're going to use some, parametric equations to describe some geometric objects. Okay, so the first section is called conics and calculus. What it means by conics is the curve you obtain when you cut some 3-dimensional objects. So for example, if you cut a cylinder with a plane, you can get 2 types or even 3 types of curves. The intersection of the plane with the surface of a cylinder. You can get a circle, or you can get a ellipse. Now, if you cut a plane with a cone, everybody knows what the cone is, in different angles, you're going to get and 2 other types of curves. Those are parabola and hyperbolic curves, right? Hyperbola. I think it's called hyperbola. Okay. So these are the types of curves you're going to get if you cut a cone with a plane. So let's just review it really quick. how to write the equation of a circle. So a circle has a center and a radius. So we call this center coordinates k and the radius r. Then the um, equation for the circle is just the x minus h squared plus y minus k squared equal to r squared. Okay, so h, k, and r, those are constants. They are fixed. X, y, these are the x and y coordinates of any point on the circle. Okay, so any point on the circle with coordinates x, y have to satisfy this equation. So that's the standard equation with the circle. And for parabola with vertex at hk, we talked about that before. And then you can write the equation of the parabola as x minus h squared equal to 4p times y minus k. Okay, so again, this h and k is the vertex of the parabola. P is another parameter also fixed as a constant, but for any particular parabola. So what is changing is just the x, y. Again, if you pick up any point on the curve on the parabola, then it has to, the x, y coordinates of the point have to satisfy this equation. Okay, so it's a little bit different from what we learned before, but you just rewrite this parabola in a little different format. There are equivalent. Okay, we just use a parameter p with some geometric interpretation. Okay, we didn't do that before, but you just rewrite in another format for the parabola or quadratic equations or functions if you want. Okay, then there are two other types of curves we didn't talk about. One is called the ellipse. So ellipse has a long axis and short axis. You see, it has a center with the coordinates hk, and we call the half length of the long axis a and the half length of the short axis b. So a typical example of ellipse, if you cut football, you're gonna get a curve like this for the intersection of the plane you cut and the surface of the football. Okay, so the standard equation of the ellipse will be x minus h squared over a squared plus y minus k squared over b squared equal to 1. Okay, again, as I said, a and b, they're half length of the long and the short axis. And h and k, they're just the x, y coordinate of the center of the ellipse. So any point on the curve on the ellipse with coordinate x, y, with coordinates x, y must satisfy this equation. Okay, and the last curve we discuss is hyperbola. It has two branches. So again, it has a center with xy coordinate hk, and it also has two axes, 2a and 2b, and they have the geometric interpretation as drawn in the graph. So you just draw the asymptotic or the lines, asymptotic lines, the two curves. You get it, something like this, and then you just draw the rectangle centered at the HK, and then these are the geometric interpretation of this A and B. You draw the tangent lines to the two curves, okay, and then the equation for this curve will be x minus h square or a square minus y minus k square or b square equal 1. So you just change plus or minus from the previous equation of ellipse. You change the shape of the curve completely. You got two branches. So any point on on the curve with coordinate x, y have to satisfy this equation. A and b, these are constants. They're fixed for any specific hyperbola, and with defined axis length to A and to B. So these are the four types of curves we talk about. Cutting from cones. We call them conics. All right. So that's the end of this section